A galaxy looks like a perfect cosmic bullseye floating in the void. This is the Cartwheel Galaxy, one of the most bizarre and visually striking objects ever seen. A masterpiece forged by a violent collision of unimaginable scale. By the end of this journey, you will understand the 25 strangest secrets that make this celestial wheel spin. We will uncover why its brilliant core seems to be missing and what monstrous objects lurk within its fiery rings. What does such a distant cataclysm reveal about the story of our own home in the stars? That iconic bull's-eye shape is the first and most profound mystery of the Cartwheel Galaxy. It is not a spiral with graceful arms pinwheeling from a bright hub. It is not a featureless elliptical, a smooth cloud of ancient stars. It is a perfect ring, a cosmic ripple frozen in time and space. This structure is defined by two distinct bands of light. At its heart lies a brilliant inner ring, a tight circle of intense blue-white radiance. Surrounding it is a broader, more diffuse outer ring, a fainter halo that completes the target-like appearance. The sheer precision of these circles defies the chaotic nature of the cosmos, pointing to a single, catastrophic event. The leading explanation is as violent as it is elegant. Astronomers believe that several 100 million years ago, a smaller companion galaxy dared to plunge directly through the heart of what was once a normal spiral galaxy. Think of it not as a glancing blow, but a direct hit, like a bullet passing through the center of a spinning wheel. This unimaginable collision sent powerful shockwaves racing outward through the galactic disk, much like the ripples that expand when a stone is dropped into a still pond. These waves compressed vast clouds of gas and dust, triggering a firestorm of new star birth. The inner and outer rings we see today are essentially the crests of those ancient shockwaves, brilliant bands where star formation was ignited in a synchronized, expanding wave. The entire galaxy became a snapshot of a single moment of destruction and creation. This leads us directly to the second great puzzle, the ghost at the center of the wheel. Most large galaxies, including our own Milky Way, possess a brilliant, tightly packed core. These central bulges are often home to a supermassive black hole, a gravitational titan that can shine with ferocious energy as matter falls into it. Yet when you look into the heart of the cartwheel, you find not a blazing beacon but a dim and diffuse glow. The core is missing, or at the very least it has been switched off. It is as if the grand cathedral has a shadow where its altar should be. What happened to the galactic heart? The violent collision that created the rings may hold the answer. One theory suggests the smaller intruder galaxy did not just pass through the disk. It may have plowed directly through the core itself. The gravitational turmoil of such a close encounter could have disrupted the dense cluster of stars at the center, scattering them and perhaps even starving the central black hole of the gas it needs to shine. In an even more dramatic scenario, the physics of the collision might have been so extreme that it ejected the supermassive black hole entirely, hurling the galaxy's heart into the dark intergalactic void. Alternatively, the core may not be gone but merely hidden. The collision would have churned up colossal amounts of gas and dust, and much of it could have settled back into the center, creating a thick, opaque shroud. Our optical telescopes see only the visible light, which is easily blocked. To solve this mystery, astronomers turn to other eyes. Infrared telescopes can peer through the dust, sensing the heat of hidden stars. X-ray observatories search for the high-energy signature of matter screaming into a hidden black hole. The hunt for the cartwheel's hidden heart is ongoing, a detective story written in wavelengths of light invisible to our own eyes. That missing core is not the only source of the cartwheel's brilliant light. Look instead to the inner ring, a searing band of blue-white fire that defines the galaxy's face. This is not a gentle nursery for stars, it is a starburst ring, a cosmic firestorm of creation. Here, the shockwave from the ancient collision did more than just ripple outward. It compressed the galaxy's vast reservoirs of hydrogen gas to an incredible density, forcing them to collapse under their own gravity. The result is a frenzied, almost violent birth of new suns. While our own Milky Way galaxy forms perhaps 1 or 2 new stars each year, this ring is a factory operating at a fever pitch. Astronomers estimate it forges new stars at a rate hundreds of times faster. Imagine the entire output of our galaxy, an entire year's worth of stellar births happening here in a single day. This furious activity populates the ring with the most massive and short-lived stars in the universe, the brilliant blue O-type giants. These are stellar behemoths, burning their nuclear fuel with such ferocity that they shine with a light millions of times brighter than our Sun, but live for only a few million years before exploding in spectacular supernova. Their intense ultraviolet radiation ionizes the surrounding hydrogen gas, causing it to glow with a characteristic pinkish-red hue. Through telescopes, these glowing clouds, known as H2 regions, appear like brilliant knots and bubbles studded along the ring, transforming it from a simple band of light into a necklace of cosmic diamonds, each gem a colossal stellar nursery shining against the dark velvet of space. The furious starburst ring we see today is a direct echo of that initial, universe-shaking impact. The physics behind it are as elegant as they are violent. When the smaller galaxy tore through the Cartwheel's heart, it unleashed a titanic shockwave, a wall of pure energy that began racing outward through the galactic disk. This was not a gentle expansion, it was a supersonic tsunami moving at hundreds of thousands of kilometers per hour. Picture the sharp crack of a sonic boom, but on a scale so vast it would take light itself tens of thousands of years to cross it. As this colossal wave front expanded, it did not travel through empty space. It plowed through the galaxy's own immense reservoir of diffuse gas and dust. The wave acted like a cosmic snowplow, sweeping up this material and pushing it ahead, compressing it into an ever denser, ever-growing wall. Within that compressed wall, conditions became perfect for starbirth. The increased density allowed gravity to take hold, pulling vast clouds of hydrogen together until they collapsed under their own weight, igniting the nuclear furnaces of millions of new stars. This is why we see that brilliant ring of blue giants. It marks the precise location of that shock wave's leading edge, frozen in time. The most astonishing part is that this is not a static picture. Using the light from different elements within the ring, astronomers can actually measure its expansion rate. They have watched over years of observation as this celestial ripple continues to move outward, a living, breathing remnant of a catastrophe that unfolded hundreds of millions of years ago. The Cartwheel Galaxy is not just a snapshot of a collision. It is a slow-motion replay, giving us a front-row seat to the ongoing physics of galactic resurrection. While the inner ring blazes with newborn fire, a ghostly echo surrounds it. The outer ring of the Cartwheel Galaxy is a different world entirely, a vast and ancient halo that tells the older part of the story. This faint, sprawling structure is not a site of frantic creation, but a testament to immense gravitational disruption. Its stars are not the brilliant blue newborns of the inner ring, they are the survivors. These are the suns that were already shining in the original spiral galaxy, peacefully orbiting its center when the cataclysm struck. The collision's gravitational shockwave did not just compress gas, it acted like a cosmic slingshot on the existing stellar population. Billions of stars were not destroyed but were violently flung outward, their orbits stretched and distorted into this enormous, diffuse band. This is why the outer ring appears so patchy and irregular, its light uneven and faded. You are looking at the scattered remains of a galactic community, displaced but still shining. The contrast with the inner ring could not be more stark. Where the inner ring is a dense, coherent band of intense blue light and pink nebulae, the outer ring is a pale, fragmented ghost. Star formation here is minimal because the shockwave that triggered it has long since passed through. and most of the gas needed to make new stars was either swept inward to feed the starburst or expelled entirely. This outer structure gives us a crucial timeline. It shows us the immediate disruptive effect of the collision, the moment the galaxy's original structure was shattered. The inner ring, born from the compressed gas, came later, a secondary effect of that same event. So when you look at the cartwheel, you are seeing two distinct chapters in the same cosmic biography: the ghostly outer ring holding the memory of what was lost, and the brilliant inner ring blazing with the fury of what was reborn. But the cartwheel is more than just two perfect rings. Look closer and you will see faint lines like the spokes of a bicycle wheel, stretching from the dim core out through the brilliant inner ring and into the ghostly outer halo. These are not tricks of the light, they are real structures, and they are the sixth great mystery of this galaxy. These radial spokes are the scars of the past, the last remaining traces of what this object once was. Before the catastrophic collision, the cartwheel was likely a grand spiral galaxy, much like our own Milky Way, with majestic arms curving out from a bright center. When the smaller galaxy plunged through, the titanic gravitational forces did not erase everything. These spokes may be the tattered remnants of those original spiral arms, stretched and torn but not completely obliterated by the shockwave. They are the skeleton of the old galaxy, still visible beneath its new, ringed form. Alternatively, they could be vast rivers of dust, dark material pulled into radial streams by the chaotic forces of the impact, obscuring the light of the stars behind them. Or they might be channels where stars and gas, caught in a delicate gravitational balance, continue to stream between the inner and outer regions. Each possibility tells a different story about the violence of that day. By meticulously mapping the movement and composition of matter within these spokes, astronomers can perform a kind of cosmic archaeology. They can work backwards, using these faint lines as a guide to reconstruct the precise angle and speed of the intruder galaxy's path. The spokes are a frozen record of the collision's geometry, a blueprint that allows us to rewind the tape and see the magnificent spiral that was lost, giving us a profound connection to the galaxy's life before its transformation. The identity of the assailant is written in the sky around the wounded galaxy. If you look at a wide-field image of the cartwheel, you will see it is not floating in isolation. Two smaller, distorted galaxies keep it company, like silent witnesses to the crime. Astronomers label these companions simply as G1 and G2. One of them, almost certainly, is the intruder that changed everything. The prime suspect is the smaller, bluer galaxy positioned to the left of the cartwheel's brilliant ring. Its appearance alone is a damning piece of evidence. Unlike a calm, settled spiral, this galaxy shows a profoundly disturbed shape, stretched and warped as if it were made of taffy pulled by an immense force. Streaming away from it are faint, luminous bridges of stars and gas, structures known as tidal tails. These are the gravitational footprints of a close encounter, material ripped away as the galaxy was stretched by the cartwheel's immense gravity during its fateful plunge. The trajectory fits the story perfectly. By tracing the angle of these tails and the alignment of the cartwheel's own spokes, astronomers can reconstruct the path. The evidence points to this blue galaxy having shot through the cartwheel's center on a trajectory that is almost perpendicular to its ring, exactly the kind of bullseye impact needed to create those perfect shockwaves. But the intruder did not escape unscathed. The collision was a traumatic event for both parties. The smaller galaxy shows clear signs of its own violent past, with its structure mangled and its star formation likely triggered by the same encounter that ignited the cartwheel's ring. It is a reminder that in the cosmos, even the perpetrator bears the scars of the crime, locked forever in a gravitational dance with the masterpiece of destruction it helped to create. These cosmic scars stretch far beyond the rings themselves. If you pull back the view, the true scale of the devastation becomes breathtaking. arcing away from the Cartwheel, and its companions are immense, faintly glowing streams of stars and gas stretching across hundreds of thousands of light-years of empty space. These are the tidal tails, the eighth and perhaps most haunting phenomenon of this entire system. They are not part of the galaxy's new structure, they are what was violently ripped away from it. Picture the gravitational forces during that head-on collision not as a simple push, but as an unimaginable tidal pull. As the smaller galaxy plunged through, the Cartwheel's gravity stretched it like taffy, pulling stars and gas out in long, streaming arcs. But the Cartwheel itself suffered the same fate, its own outer regions shredded and flung into the void. These tails are the debris of that mutual destruction, a permanent record of material that was torn from its home and may never return. They are the galaxy's lost matter, glowing with the soft, collective light of billions of exiled suns and the cold gleam of scattered gas clouds. By meticulously mapping the length, curvature, and composition of these tidal tails, astronomers can perform a kind of celestial forensics. The tails act like a frozen clock. Sophisticated computer simulations can rewind their formation, testing different collision angles and speeds until the virtual recreation matches the ghostly streams we see today. This painstaking work has given us a date for the catastrophe. The best models suggest the intruder galaxy pierced the Cartwheel's heart approximately 400 million years ago. To put that in perspective, when this galactic wreckage was first forming, on Earth, simple plant life was just beginning to colonize the land. The light from that event has been traveling through space ever since, only now revealing to us a story of ancient violence written in these faint, beautiful scars. Yet amidst this grand architecture of rings and tails, the Cartwheel Galaxy holds point-like secrets that shine with a different, more dangerous light. Scattered across its structure are tiny, brilliant beacons that outshine entire star clusters, but they do not radiate in the visible spectrum we see. These are ultraluminous X-ray sources, or ULXS, and they are among the most puzzling objects in modern astronomy. Imagine finding a single, tiny light bulb in a city that is shining brighter than every street lamp, car headlight, and neon sign combined, and you begin to grasp their strangeness. These are not the gentle glow of stars, they are torrents of high-energy X-ray radiation, the kind produced by matter in the most extreme environments imaginable. What makes them so baffling is their location and their power. They are not at the galaxy's core, where a supermassive black hole could explain such fury. Instead, they are found out in the spiral arms or within the brilliant starburst ring itself, isolated points of incomprehensible violence. Their X-ray output is hundreds to thousands of times greater than anything a typical stellar black hole, the remnant of a single dead star, should be capable of producing. So what are they? Astronomers have several compelling and equally fantastic theories. One possibility is that we are looking at intermediate mass black holes, elusive cosmic middleweights with masses thousands of times that of our Sun. These would be the missing link between small stellar black holes and the supermassive giants at galactic centers, and the Cartwheel's violent history could have forged them. Another theory points to a special type of neutron star, a city-sized remnant of a supernova, with a magnetic field so unimaginably strong it acts as a funnel, allowing the star to devour matter and shine far beyond its theoretical limit. Perhaps the most intriguing idea is that these are ordinary stellar black holes caught in a moment of cosmic gluttony. If gas is falling onto them in a thick, dense disk like water pouring down a drain, the radiation pressure might not be able to push it all away, allowing the black hole to temporarily feed at a super Eddington rate, breaking its own rules and shining with forbidden brilliance. The Cartwheel Galaxy, with its abundant gas from the collision, is a perfect hunting ground for these ravenous objects, and each one we find is a clue to understanding the limits of physics under the most extreme conditions the universe can devise. The violence of creation in the Cartwheel's ring does not end with a star's brilliant birth. For the most massive of these blue giants, their fiery lives are a brief prelude to an even more spectacular death. These stellar behemoths burn through their nuclear fuel in only a few million years, a cosmic blink of an eye, before ending their existence in titanic supernova explosions. Each blast is a universe-shaking event, unleashing more energy in an instant than our Sun will produce in its entire 10 billion-year lifetime. But the story does not end with the flash. The aftermath of these explosions carves permanent scars into the fabric of the galaxy, creating the 10th strange phenomenon, the supernova remnants and the colossal structures they build. When a star explodes, it does not simply vanish. It hurls its own outer layers into space at velocities of thousands of kilometers per second. This ejected material, heated to millions of degrees, plows into the surrounding interstellar gas like a cosmic snowplow, sweeping it up into an expanding, shimmering shell. We see these shells as supernova remnants, often beautiful, delicate filaments of glowing gas that can persist for tens of thousands of years. In the crowded, frenzied environment of the Cartwheel starburst ring, these deaths are not isolated events. They are constant. So many massive stars are born so close together that their life cycles are synchronized in a grim, explosive chorus. When one star explodes, its expanding remnant slams into the remnants of its neighbors. These overlapping shockwaves combine their force, and instead of creating individual shells, they begin to excavate something far larger. They blow giant cavities in the interstellar medium known as superbubbles. Imagine not a single firecracker going off in a field, but dozens of sticks of dynamite detonating in a coordinated pattern beneath the soil. The result is not a small crater, but an entire section of the Earth heaved upward and blown outward, creating a massive, ragged hole. That is what is happening within the Cartwheel's ring. The combined fury of countless supernovae is literally sculpting the galaxy's structure from the inside out, creating vast, empty chambers surrounded by walls of compressed, glowing gas. To see this violent architecture, we must look with X-ray eyes. The Chandra X-ray Observatory has peered into the Cartwheel and revealed these superbubbles not as empty space, but as intense sources of high-energy emission. The gas inside these cavities, heated by the relentless shockwaves to temperatures in the millions of degrees, glows fiercely in X-rays. Chandra's data maps show these hot, glowing cavities peppered throughout the star-forming ring, like bubbles rising in a cosmic cauldron. They are the direct, ongoing testament to the furious cycle of life and death that defines this galaxy, a cycle where the violent end of one generation of stars clears the space and enriches the gas that will eventually collapse to form the next. These titanic collisions do more than rearrange stars and gas. They reveal the invisible architecture of the cosmos. The violent history of the Cartwheel Galaxy has turned it into a perfect natural laboratory for studying the universe's greatest mystery, dark matter. We cannot see dark matter, we cannot touch it, and it does not emit or reflect any form of light we can detect. We only know it exists because of its immense gravitational pull, a ghostly force that holds galaxies together and governs the motions of stars. When the smaller galaxy smashed through the Cartwheel, it created a cosmic experiment on a grand scale. Normal matter, the gas and dust that make up stars and planets, collides and interacts. It feels friction, it compresses, it heats up and it glows, which is exactly why we see those brilliant rings of star formation. But dark matter is thought to be fundamentally different. It does not interact with light or with itself in any way we understand. It only feels and exerts gravity. So during that catastrophic collision, the dark matter associated with each galaxy should have behaved in a profoundly strange way. Picture two crowds passing through each other in a fog. The people, representing stars and gas, would bump into each other, slow down, and get tangled. But the fog itself, representing the dark matter halos surrounding each galaxy, would simply pass through without slowing, without interacting at all. This means the distribution of dark matter in the Cartwheel today might tell a completely different story than the visible rings and spokes. Astronomers are actively hunting for this ghostly signature. They meticulously map the motions of stars and gas clouds throughout the galaxy, measuring their speeds and trajectories with extreme precision. These motions are dictated by the total gravitational pull they feel, a pull that comes from both the visible matter and the vast, unseen dark matter halo. By subtracting the gravitational influence of all the bright material they can see, they can infer the shape and location of the invisible dark matter. The central question is haunting. Did the dark matter halo stay perfectly centered, anchored by its own immense gravity while the visible galaxy was ripped apart around it? Or was it also distorted, dragged slightly off-center by the gravitational turmoil of the impact? The answer would tell us fundamental things about the nature of dark matter itself. Is it truly as non-interactive as we think, or does it have some subtle, unknown properties that allow it to feel a drag? Every measurement of a star's path in the Cartwheel is a data point in this grandest of experiments, an attempt to map the shadow skeleton of a galaxy rebuilt by fire. The violence of stellar life and death does more than sculpt the galaxy's shape. It fundamentally changes its ingredients. Within the swirling gas of the Cartwheel, astronomers have detected a strange chemical fingerprint, a story written not in light, but in the very elements that make up the cosmos. This is the phenomenon of metallicity, a term that sounds simple but holds profound meaning. In astronomy, a metal is not just iron or gold. It is any element heavier than the primordial hydrogen and helium born in the Big Bang. Every carbon atom in your body, every speck of oxygen you breathe, every particle of silicon in a grain of sand was forged in the heart of a star and scattered into space by its explosive death. A galaxy's metallicity is therefore a record of its industrial history, a logbook of how many generations of stars have lived, died, and enriched their surroundings. In a calm, ancient galaxy like our Milky Way, this enrichment has happened steadily over billions of years, creating a relatively uniform mix, but the Cartwheel is not calm. Its history is a sudden, violent explosion of industry, and that should leave a very distinct chemical signature. The expectation was clear. The inner starburst ring, the site of frantic star birth and countless supernova, should be a factory for heavy elements. All that furious activity should have cooked the surrounding gas, seeding it with a rich abundance of metals, making it chemically mature. The outer ring, made of older, displaced stars from the original galaxy, might show a different, perhaps more primitive composition. But when scientists pointed their spectrographs, instruments that can dissect light into a chemical barcode, the picture that emerged was more nuanced and revealing. The data suggested the inner ring's gas is indeed enriched, but not in a perfectly uniform way. Some areas blaze with the signature of oxygen, neon, and sulfur, elements spewed out by massive stars and their supernova deaths. Other regions show a surprising deficit. This patchwork quilt of chemistry tells us the mixing is incomplete. The supernova bubbles and stellar winds have not yet had time, even over hundreds of millions of years, to completely stir the galactic pot. Fresh, unprocessed hydrogen from the outer regions may still be funneling in, diluting the mix. Meanwhile, studies of the suspected intruder galaxy show its own distinct chemical makeup, different from the Cartwheel's rings. This is a crucial clue. If the two galaxies had fully merged and their gases completely mixed, their metallicities would have blended into one. The fact that they remain chemically distinct tells us this was a high-speed, piercing collision, a hit and run that stirred the pot violently but did not allow time for a full, homogeneous blend. Each element becomes a tracer, a tag following a specific path from its birth in a star to its final resting place in the galactic gas. By mapping where iron shines brightly and where it is faint, astronomers can literally watch the fallout from ancient supernovas still settling, painting a dynamic picture of a galaxy whose very atmosphere is still churning with the echoes of its rebirth. That chemical fingerprint of unmixed elements points to a deeper structural mystery within the Cartwheel's anatomy. Beyond its two famous rings, some astronomers suspect the galaxy might be hiding a third, even more peculiar structure, one that orbits at a right angle to everything else. This is the suspicion of a polar ring, a halo of gas and stars circling over the galaxy's poles like a brim around a hat. Most galaxies rotate with their stars and gas moving in a relatively flat disk like a spinning vinyl record. A polar ring defies this logic, orbiting perpendicular to that main disk, tracing a path that goes over the galactic north and south poles. These structures are incredibly rare and are thought to form when a smaller galaxy is torn apart and its remains are captured into a perpendicular orbit. For the Cartwheel, the evidence is subtle but compelling. The orientation of the faint outer ring and the motions of certain gas clouds measured by radio telescopes do not perfectly align with the plane of the main galaxy. Some streams of material appear to be moving on a different, highly inclined trajectory. If confirmed, this would add a staggering layer of complexity to the collision narrative. It would suggest the intruder galaxy did not just come in on a simple, piercing path through the disk. Instead, its approach might have been a precise, glancing blow that sent a portion of its debris into a tilted, stable orbit. Alternatively, the polar ring could be the ghost of a second, entirely separate event. Long after the main collision that created the brilliant rings, another small galaxy or a massive gas cloud might have been captured by the Cartwheel's gravity, slowly being shredded and woven into this perpendicular halo. This would mean the Cartwheel is not a snapshot of one catastrophe, but a palimpsest, a cosmic document where the story of multiple violent encounters has been written over time. Each strange motion of gas, each faint stream of stars out of alignment, becomes a potential clue in solving this three-dimensional puzzle, forcing us to reconsider if we are looking at the aftermath of one crash or a series of collisions that have left this galaxy spinning in more ways than one. The Cartwheel's brilliant firestorm cannot burn forever. All that furious star formation comes at a terrible cost, consuming the galaxy's most precious resource at a staggering rate. The brilliant blue giants of the inner ring are not just massive, they are gluttonous, devouring the hydrogen gas around them at a pace that is utterly unsustainable. This is a galaxy living in a state of cosmic fever, and like any fever, it must eventually break. The fate of the Cartwheel is written in the dwindling reserves of its own fuel. Over the next several 100 million years, the starburst will begin to sputter and die. The most massive stars will have already exploded, and without a fresh influx of dense gas, new stars will simply stop forming. The pink glow of the nebulae will fade, and the searing blue light of the ring will soften, dimming as the remaining stars age into cooler, redder giants. The sharp, defined rings we see today will slowly blur and diffuse over billions of years, their structure softened by the gravitational tug of stars and the gentle mixing of time. But the story does not end with a quiet fade to black. The gravitational drama that started it all is still playing out. The Cartwheel and its two companion galaxies, including the suspected intruder, are locked in a slow, intricate dance. Computer simulations of this celestial trio paint several possible futures. In one common scenario, the smaller galaxies, already gravitationally bound, will continue to loop around the Cartwheel, their orbits slowly decaying. Over many billions of years, they will spiral inward, drawn by relentless tidal forces, and finally merge with the larger galaxy in a second, slower but no less transformative collision. This merger, WOULD Chinese letter stir the remaining gas and stars, likely erasing the last vestiges of the ring structure entirely. The end product would not be a majestic spiral or a perfect ring, but a more common, featureless elliptical galaxy, a smooth, golden haze of old stars, a quiet retirement home for a once violent masterpiece. Alternatively, the gravitational interactions could be more chaotic. A close pass might fling one of the smaller companions out into the void entirely, ejecting it from the system on a one-way journey into intergalactic space. The Cartwheel, robbed of its partners, would then evolve in isolation, its rings slowly fading into a more irregular, lumpy shape. No matter the precise path, the ultimate lesson is one of cosmic impermanence. The Cartwheel Galaxy is a temporary spectacle, a brilliant flash in the dark. We are witnessing it in its most dynamic, explosive phase, a phase that occupies only a tiny sliver of its multi-billion-year life. Its fate reminds us that the universe is in constant, slow-motion flux, where even the most stunning and strange structures are merely waypoints in an endless journey of change. Its immense mass offers another way to see the unseen. The Cartwheel Galaxy's colossal collection of stars, gas, and dark matter creates a gravitational field so powerful it can bend the very fabric of space-time around it. This leads us to a subtle but profound phenomenon, the possibility of gravitational lensing. Picture gravity not just as a pull, but as a curvature. A massive object like a galaxy sits in space like a heavy ball placed on a stretched rubber sheet, creating a deep well. When light from a far more distant object travels through this warped space, its path is bent, just as a marble would curve rolling past that depression. This is gravitational lensing, nature's own telescope, where a foreground galaxy can magnify, distort, and even multiply the image of a galaxy billions of light years behind it. For the Cartwheel, with its unique mass distribution from the collision, this presents a fascinating test. Its mass is not smoothly spread out, it is concentrated in those dense rings and its mysterious core. Could this peculiar architecture create detectable lensing effects? Astronomers have scanned the regions around the Cartwheel's edges, looking for the telltale signs, faint arcs of distorted light or strangely duplicated points that would betray the presence of an even more distant galaxy glimpsed through this cosmic lens. So far, no strong, obvious lens has been identified, which is itself an important piece of data. It suggests that while the Cartwheel is massive, its mass may be too diffuse or not aligned precisely enough with a brilliant background object to create a dramatic lens. But the search continues with ever more sensitive instruments. Finding even a weak lensing signal would be a treasure trove. It would provide an independent way to map the galaxy's total mass, including its dark matter halo, confirming or challenging the measurements made from stellar motions. The absence of a lens helps us understand the geometry of the collision, telling us how the mass is truly arranged in this celestial wreckage. Every photon of light skimming past the Cartwheel's rim carries a story, and some of those stories may be from universes beyond our own, subtly rewritten by the galaxy's invisible hand. The Cartwheel's violent history is not just written in light, gas, and gravity. There is an invisible force woven throughout its structure, a silent, pervasive presence that shapes its destiny. This is the galaxy's magnetic field, a vast and delicate web of energy that threads between the stars. In our own Milky Way, these fields are relatively weak but crucial, guiding the flow of gas and influencing where new stars can form. But what happens to this magnetic tapestry when a galaxy is struck by a cosmic bullet? The collision that created the Cartwheel's rings would have done more than shock the gas. It would have violently twisted and stretched these magnetic field lines, potentially amplifying them to extraordinary strength. The shock wave that compressed the gas into the brilliant starburst ring likely did the same to the magnetic field, squeezing and aligning the invisible lines of force until they ran like rails along the ring itself. A stronger, more organized magnetic field in that region could act as a cosmic containment system, helping to channel turbulent energy and even trap the high-energy particles we see as cosmic rays. But how do you measure something you cannot see across millions of light years? Astronomers turn to a special kind of radio whisper. They use enormous radio telescopes to listen not just for any emission, but for a specific signal called polarized radio waves. When fast-moving electrons, accelerated by supernova shocks, spiral around magnetic field lines, they emit a faint radio glow. If the magnetic field is orderly, this emission becomes polarized, meaning the radio waves vibrate in a preferred direction. By meticulously mapping the direction and strength of this polarized signal across the cartwheel, scientists can essentially trace the invisible magnetic architecture. It is like watching iron filings align around a magnet, but on a galactic scale. The resulting map would show us where the field is chaotic and tangled from the ancient turmoil, and where it has been combed straight and strong by the expanding shockwave in the ring. Understanding this magnetic skeleton is vital. It tells us how energy from supernova is transported throughout the galaxy, how cosmic rays are accelerated to near-light speeds, and whether these fields can actually help or hinder the next generation of star birth by providing support against gravitational collapse. The cartwheel's magnetic field is the silent conductor of its ongoing symphony of creation and destruction, an unseen hand guiding the fallout of that ancient crash. The magnetic fields threading the cartwheel's rings are not the only structures forged under extreme pressure. Within the searing blue band of star formation, astronomers suspect the existence of stellar cities of almost unimaginable density. These are superstar clusters, and if present, they are among the most brilliant and crowded neighborhoods in the entire galaxy. Picture not a loose scattering of stars, but a single, titanic cloud of gas compressed by the galactic shockwave to its absolute breaking point. Instead of collapsing into a few dozen stars, it gives birth to hundreds of thousands all at once in a single, furious burst of creation. The result is a dazzling, compact sphere of stellar fire, a single point of light that can outshine entire small galaxies. In the Cartwheel starburst ring, such clusters would not be rare curiosities. They would be the dominant source of light, the brilliant jewels that make the ring itself shine so fiercely. Each one is a cosmic time capsule, offering us a living glimpse into the distant past of our own home. The ancient globular clusters that orbit the Milky Way, dense balls of 1 million stars each, are some of the oldest objects in the universe. Their individual stars are so ancient and crowded together that we have never been able to see one form. They are fossils from the universe's violent youth. But here, in the Cartwheel, we may be witnessing that exact process in real time. The superstar clusters blazing within its ring are likely the infant versions of those same globular clusters. By studying their size, their brightness, and the types of stars within them, we are watching the recipe for building these celestial relics unfold before our eyes. We see how a single, monstrous cloud fragments into a bound family of stars that will remain gravitationally tied together for billions of years, surviving the galaxy's ongoing turmoil. Each cluster is a laboratory for stellar evolution on a grand scale, a chance to understand how the universe's first magnificent structures were assembled in the fires of creation. The ferocious energy of the Cartwheel starburst does not remain neatly contained within its rings. It erupts violently into the void. Across the galaxy, astronomers have detected immense clouds of gas screaming through space at speeds exceeding 1 million kilometers per hour. These are not the gentle, orbiting rivers of a calm galaxy. They are supersonic cannon shots, and they are the 18th strange phenomenon reshaping this cosmic wheel. Some of these high-velocity clouds are likely stragglers, material from the ancient tidal tails still falling back into the galaxy, pulled in by its immense gravity like celestial rain. But many others are being actively blasted outward, a direct product of the ring's relentless fury. Imagine the combined might of 1 million stellar hurricanes. The most massive stars in the ring do not burn quietly. They unleash torrents of charged particles, a constant, powerful stellar wind. And when these stars inevitably die in supernova explosions, the blast waves add an unimaginable shove. Together, these forces create a galactic wind, a vast, high-pressure front of superheated gas that can overcome the galaxy's own gravity and blow its very substance out into the emptiness between galaxies. But how do we measure the speed of something so distant and intangible? The answer is written in the light itself, in a cosmic barcode known as a spectrum. When astronomers point their telescopes at a specific cloud, they use an instrument called a spectrograph to split its faint glow into a rainbow of colors. Imprinted on that rainbow are dark or bright lines, the unique fingerprints of elements like hydrogen, oxygen, and iron. Here is the crucial part. If the cloud is stationary relative to us, those lines will appear at very specific known wavelengths. But if the cloud is rushing toward us or away from us, the lines shift. Motion toward us squeezes the light waves, shifting the lines toward the blue end of the spectrum. Motion away stretches the waves, shifting the lines toward red. This is the Doppler effect, the same principle that makes a siren's pitch change as it speeds past you. By measuring precisely how far these spectral lines have shifted from their expected positions, astronomers can calculate the cloud's velocity with stunning accuracy. The readings from the Cartwheel show these dramatic shifts, confirming gas clouds are being ejected at breathtaking speeds. This process is a galactic exhalation, and it has profound consequences. These high-speed clouds carry with them the heavy elements forged in the ring's stellar furnaces: carbon, oxygen, iron, seeding the barren intergalactic medium with the very seeds of future planets and life. They are also a form of cosmic feedback, robbing the galaxy of the fuel it needs to make the next generation of stars, ultimately helping to end the very starburst that created them. The Cartwheel is not just a beautiful ring, it is a powerful engine blowing its own substance into the cosmic wind. That torrent of gas and dust blown from the starburst ring is not lost to darkness. It glows with a hidden fire, revealing a deeper layer of the Cartwheel's furious activity. This galaxy is not just brilliant in the visible light our eyes can see. It is a beacon in the infrared, shining with an intensity that betrays the true scale of its hidden industry. All those newborn stars blazing in the blue ring do more than emit visible light. They flood their surroundings with intense ultraviolet radiation. This energetic light does not simply travel through space unhindered. It slams into the microscopic grains of dust that fill the galaxy, dust churned up by the collision and enriched by supernova explosions. These tiny particles absorb that stellar energy, heating up until they themselves begin to glow, not with visible light but with a warm, pervasive infrared radiance. It is the same principle as a piece of metal left in the sun. It grows warm to the touch, emitting heat you can feel but not see. For the Cartwheel, this effect is magnified on a galactic scale. The dust is everywhere, shrouding the very heart of star formation. While optical telescopes like Hubble show us the brilliant blue light that escapes the dust clouds, they miss the colossal factories operating behind those sooty curtains. This is where telescopes like the retired Spitzer Space Telescope and now the James Webb Space Telescope become our essential guides. Their infrared eyes are perfectly tuned to sense this heat signature. They peer straight through the veils of dust that block visible light, revealing a hidden universe of stellar nurseries that optical images can only hint at. The picture that emerges is staggering. The Cartwheel's total star formation rate, when measured by this infrared glow, is likely even more extreme than the already frantic pace we inferred from its blue light alone. We are not just seeing the stars that manage to shine through the dust. We are sensing the collective warmth of billions more infant suns still cocooned in their natal clouds, their visible light completely absorbed and transformed into this telltale infrared heat. This hidden brightness forces us to revise the galaxy's entire energy budget, understanding that what we see with our traditional eyes is merely the tip of a fiery, dusty iceberg. These brilliant blue knots are not just abstract points of light, they are individual cities of creation. Peering into a high-resolution image from the Hubble or James Webb Space Telescope, the Cartwheel's inner ring resolves into a breathtaking string of cosmic pearls, each one a distinct and monstrous stellar nursery. These are the blue knots, and their intricate structure tells the story of the shockwave's power in exquisite detail. A single knot is not a uniform blob. At its heart, you often find a dazzling, concentrated cluster of newborn stars, shining with such ferocious blue-white intensity that they can outshine entire smaller galaxies. This central core is the engine of the knot, a gravitational anchor. Radiating outward from it are vast, complex nebulae, glowing in vivid pinks and reds from the intense ultraviolet light of those central stars. And weaving through this luminous gas are intricate, dark filaments and lanes. These are the dense, cold clouds of dust and gas that have not yet been consumed by star formation, the raw material for future generations. The sheer size of these knots is staggering. A single one can span over 1,000 light-years from end to end, a volume of space that could contain our entire local stellar neighborhood many times over. Their spacing along the ring is not random, it is a direct physical record. The shockwave that created the ring did not move as a perfectly smooth wall. Instead, it likely propagated through a pre-existing, lumpy medium of gas. Where the gas was already slightly denser, the shock compressed it even more fiercely, triggering these especially massive bursts of star formation. The consistent distance between these brilliant knots gives astronomers a way to measure the properties of that ancient wave: its speed, its stability, and the density of the galactic disk it traveled through. They are like buoys left floating on the surface of a pond after a stone was dropped, marking the precise pattern of the initial disturbance. Watching how these knots evolve, some perhaps merging, others fading as their stars explode, allows us to see the shockwave's legacy not as a single event, but as a chain reaction of fires, each igniting the next in a slow, majestic burn across the face of a galaxy. The debris flung from the cartwheel is more than just scattered wreckage. Within those vast, arching tidal tails, some of the densest knots of gas and stars may be struggling to achieve their own independence. Astronomers call these potential objects tidal dwarf galaxy candidates, and their existence would transform our view of galactic collisions from pure destruction to a strange kind of creation. These are not galaxies that existed before the crash. They are entirely new structures being born from the expelled material. The key to their identity lies in a delicate balance of forces. For a clump in a tidal tail to become a true dwarf galaxy, it must achieve self-gravitation. This means the mutual gravitational pull of all the stars and gas within the clump must be strong enough to hold the object together against the tidal forces trying to rip it apart. Imagine a small ball of wet clay being spun on a string. If the clay is too loose, it flies apart into specks, but if it is kneaded into a dense, cohesive mass, it holds its shape as it spins. That is the struggle happening within the cartwheel's tidal streams. Astronomers search for these candidates by looking for the densest, brightest condensations within the tails. They then measure two critical things. First, they calculate the mass of the clump from its brightness and the motion of its gas. Second, they estimate how much of that mass is likely made up of dark matter. This is the crucial test. Large primary galaxies like the Cartwheel are embedded in huge halos of dark matter, but during a collision, the dark matter, which does not interact, largely passes through without getting caught in the tidal debris. Therefore, a true tidal dwarf galaxy, born from the collisional debris of stars and gas, should be made almost entirely of normal, visible matter. It should be curiously lacking in dark matter, a trait that would make it utterly unique in the cosmos. So, do any of the knots around the Cartwheel meet these strange criteria? Detailed studies have identified several promising, bright condensations within its magnificent tidal tails. Their masses are significant, some containing the equivalent of hundreds of millions of suns. The ongoing analysis is a cosmic audit, trying to determine if their gravity is supplied solely by the glowing material we can see. If confirmed, these objects would be living proof that a titanic collision can act as a galactic foundry. forging entirely new, albeit smaller, island universes from the ashes of the old. These nascent dwarfs would then orbit their colossal parent for billions of years, a permanent, shining testament to the day a galaxy was torn apart and from its pieces new worlds were born. The Cartwheel Galaxy is a target that never holds still. This celestial wheel is not a static portrait, but a dynamic arena where cataclysmic events unfold on a regular timeline. With such a furious rate of star birth and death, the galaxy offers a rare front row seat to the most violent stellar explosions in the universe. Astronomers, both professional and amateur, occasionally witness the brilliant flash of a supernova within its rings, a single star ending its life with a burst of light that can briefly outshine its entire host galaxy. These are not predictable events, they are transient phenomena, sudden and dramatic changes in the night sky that vanish almost as quickly as they appear. Catching one requires patience and constant vigilance, turning the cartwheel into a prized cosmic watchtower. But supernovae are not the only sources of variability. Remember those mysterious ultraluminous X-ray sources, the ULXS, scattered across the galaxy. These enigmatic objects are notorious for their flickering behavior. They can flare up in X-ray brightness by orders of magnitude over days or weeks, then fade back into obscurity. This variability is a crucial clue to their nature. A sudden brightening might signal a massive influx of gas onto a hidden black hole or neutron star, a stellar companion shedding its outer layers in a doomed dance. Each flicker, each spike in the data, is a message about the extreme physics governing matter at the brink of oblivion. This inherent unpredictability makes the cartwheel a living laboratory. Observatories around the world and in space regularly train their instruments on it, not just to study its permanent structures, but to catch it in the act of change. For an amateur astronomer with a capable telescope and camera, monitoring this distant galaxy night after night is a genuine contribution to science. You are not just looking at a beautiful picture, you are participating in a watch. A single new point of light in the spiral arm, a subtle brightening in one of the blue knots, could be the discovery of a stellar cataclysm millions of years in the past, its light only now reaching our eyes. In this way, the cartwheel connects us directly to the real-time drama of the cosmos, reminding us that the universe is a place of constant, explosive transformation. Each of those transient flashes tells only one small part of the cartwheel's epic. To truly understand this galactic wheel, we must learn to see it through different eyes. The iconic, colorful portrait from optical telescopes like Hubble is breathtaking, but it is just one chapter in a much longer book. The full story of the cartwheel is written across the entire electromagnetic spectrum, and each wavelength of light reveals a different layer of its anatomy. Let's take a comparative tour, starting with the coldest whispers. In radio waves, the cartwheel transforms. The brilliant blue knots and pink nebulae fade away, replaced by a map of cold, neutral hydrogen gas. This view traces the raw fuel of the galaxy, showing vast reservoirs swirling in the rings and stretching out into those faint tidal tails. It can also reveal the ghostly imprint of magnetic fields, showing where those invisible lines are stretched and ordered by the shockwave. Switch to the infrared and the galaxy glows with a warm, dusty light. Here, the piercing blue light of the hottest stars is subdued. Instead, we see the searing heat of dust grains baked by starlight, illuminating the hidden nurseries where stars are still cocooned in their birth clouds. The galactic core, so dim in optical light, often brightens in the infrared, hinting at shrouded activity. The classic optical view is the one we know best: the sharp rings, the blue star clusters, the pink emission nebulae. It shows us the galaxy's visible face, the light our own eyes would see if we were close enough, but move to the ultraviolet and the image sharpens with fierce intensity. Only the very hottest, most massive and short-lived stars emit strongly here. The ultraviolet view strips away the older, cooler stars and the glowing gas, leaving behind a skeleton of the starburst ring itself, a stark map of where stellar birth is most violent and recent. Finally, we look with X-ray eyes. In this high-energy band, the calm beauty vanishes entirely. The cartwheel becomes a battlefield. Glowing dots scattered across the rings mark the locations of those mysterious ultraluminous X-ray sources, black holes or neutron stars feasting on companions. Vast, diffuse clouds of superheated gas with temperatures in the millions of degrees fill the superbubbles blown by countless supernovae. This is the aftermath of stellar violence, the searing echo of the galaxy's furious energy. None of these views is the true Cartwheel Galaxy. The cold radio gas, the warm infrared dust, the brilliant optical stars, the fierce ultraviolet beacons, and the searing X-ray aftermath, they are all real, all happening at once in the same place. Only by weaving these disparate visions together do we begin to comprehend the full, magnificent complexity of this cosmic wheel. It is a living reminder that the universe is a symphony, and to hear it, we must listen to every note. These multi-wavelength portraits of the cartwheel are not just observations, they are the ultimate test for a profound scientific process. To truly understand that ancient catastrophe, we must attempt to recreate it not with telescopes but with pure mathematics and silicon. This is the world of cosmological simulations, where supercomputers serve as time machines, running the laws of physics backward and forward to solve the greatest mystery of all: what exactly happened that day. The goal is deceptively simple. Start with a model of a spiral galaxy, send a smaller galaxy hurtling toward it, and let gravity, hydrodynamics, and stellar evolution play out over hundreds of millions of simulated years. The challenge is everything in the details. Scientists must input a dizzying array of variables: the precise mass of the original spiral, the size and density of the intruder, the speed of its approach, and the all-important angle of impact. A direct head-on bullseye strike produces a cleaner ring, while a more glancing blow might create a lopsided or broken structure. The simulations then animate these possibilities before our eyes. We watch as the digital intruder plunges through the disk, sending shimmering shockwaves rippling outward. We see tidal tails form like strands of cosmic taffy, and we witness the brilliant ring of star formation ignite in the compressed gas. The most advanced simulations are breathtakingly detailed, tracking not just the motion of stars but the churning of gas, the formation of individual star clusters, and the feedback from supernova that can blow cavities in the newborn ring. Each run is a unique experiment, a what-if scenario for the universe. The crucial moment comes when the simulation finishes and the final frame, a synthetic image of the resulting galaxy, is placed side by side with the actual Hubble and James Webb Space Telescope portraits of the cartwheel. This is where theory meets reality. Do the simulated rings have the same sharpness, the same ratio of inner to outer diameter? Do the tidal tails curve with the correct graceful arc? Is the distribution of bright blue knots along the ring a match? The answer is a fascinating and iterative yes and no. Early simulations produced beautiful rings, but they often appeared too perfect, too symmetrical compared to the slightly lumpy, complex reality of the cartwheel. This mismatch was not a failure, it was a clue. It told scientists their initial assumptions were too simple. Perhaps the original galaxy was not a pristine spiral, but already had a clumpy, irregular gas distribution. Maybe the intruder galaxy was not a simple sphere of stars, but had its own complex structure that influenced the debris. Or perhaps multiple close encounters were needed to explain the faint spokes and potential polar ring. Each discrepancy forced a refinement, a tweak to the digital recipe. The simulations are not a one-time recreation, they are a dialogue. The real galaxy asks a question, and the simulations propose an answer. When the answer does not fit perfectly, the question gets sharper. This back and forth has slowly converged on our current best model, a moderately sized companion galaxy piercing the Cartwheel's disk at a high speed, nearly perpendicular to its plane around 400 million years ago. The match today is remarkably good, but it is not perfect, and that imperfection is the engine of discovery. It means there are still secrets hidden in the Cartwheel's light, details we have not yet measured precisely enough, or physical processes in the simulation we have not yet modeled with enough fidelity. Every new observation, every fresh infrared glimpse from Webb, provides more data to feed back into the digital universe, tightening the loop between what we see and what we can recreate. This is the heartbeat of modern astrophysics, a constant, thrilling dance between the unyielding reality of the cosmos and our relentless attempt to code its story. The Cartwheel story is far more than a single, spectacular accident. It is a masterclass in galactic evolution, a vivid demonstration that the lives of galaxies are not always slow, stately dances. Sometimes they are punctuated by violent, transformative collisions that rewrite their entire future in a cosmic instant. This single object synthesizes all the strange phenomena we have explored, from its missing core to its supersonic winds, into a crucial case study. It shows us with stunning clarity how a major interaction can shatter a spiral's graceful form, compress its gas into a firestorm of creation, and forge an entirely new architectural type, the ring galaxy. This is not a gentle process of aging. It is a sudden, feverish rebirth triggered by catastrophe. The Cartwheel proves that galaxy evolution operates on multiple timelines, the slow creep of internal processes, and the abrupt, revolutionary shock of a collision. This understanding casts a revealing light much closer to home on our own galactic neighborhood. The Milky Way and Andromeda galaxies are on a collision course, destined to meet in a titanic merger billions of years from now. While it likely will not create a perfect ring like the Cartwheel, the geometry and conditions will be different, the fundamental physics will be the same. We will witness from within the same chain of events, gravitational turmoil stretching stars into tidal tails, shockwaves compressing gas to ignite starbursts, and the eventual blending of two distinct systems into a single new entity. The Cartwheel Galaxy, therefore, is not just a distant wonder. It is a prophetic glimpse, a time-lapse preview of a possible future written in the stars above us. It teaches us that our quiet corner of the cosmos is not immune to the grand, violent, and beautiful forces that continually reshape the universe. From the perfect bullseye of its colossal rings to the ghostly whispers of its missing heart, we have journeyed through 25 of the Cartwheel Galaxy's deepest mysteries. We have seen how a single, violent impact forged a masterpiece of destruction and creation, igniting a firestorm of starlight, scattering tidal tails across the void, and seeding the darkness with enigmatic black holes and the potential birth of new dwarf galaxies. Each phenomenon, from the supersonic galactic winds to the hidden infrared glow, is a single thread in a magnificent cosmic tapestry woven together by the relentless laws of physics. The Cartwheel is not a static portrait hanging in a museum of the cosmos. It is a living, breathing, evolving entity, a slow-motion replay of a catastrophe that continues to shape its destiny millions of years later. It reminds us that the universe is a dynamic and often violent artist, capable of using chaos as a brush to paint structures of breathtaking beauty and profound strangeness. These distant events are more than just spectacular shows. They are fundamental chapters in the story of how galaxies live, collide, and are reborn. They help us decipher the past of our own Milky Way and imagine its possible future. I would love to hear which of these 25 strange phenomena captured your imagination the most. Was it the monstrous ultraluminous X-ray sources, the ghostly spokes, or the idea of entire new galaxies being born from the debris? Let me know in the comments below. If you enjoyed this deep dive into cosmic mysteries, please give the video a like and subscribe for more journeys to the furthest reaches of space.